Hello, AP Physics 1 students. I'm going to be leading you through problem 4 in your rotational dynamics packet, so please have that in front of you. In class, we had just barely gotten through part A and a little bit into part B, but we sort of rushed through it. So I'm going to take it step by step from the very beginning, in case it went through a little too quickly. So we're starting here looking at the Atwood machine. We've seen this idea before, where we have the two masses connected by a massless string over a massless pulley. At least that's what we're going to pretend was happening in part A. It's our old stuff where everything's done like normal. So since we have the system connected masses, we can use the system equation, sigma F external equals total mass times acceleration. At this point in the year, you should be really good at identifying where the external forces are. In this case, it's only the weights of the two masses. The tension in the string between them is what's called an internal force. And so the competing forces are the weight of the heavier mass, that's M2G, and that's going to try to rotate the pulley, rotate the system clockwise, as opposed to M1G, which is pulling the other way, trying to rotate the system counterclockwise. And since M2 is larger than M1, which it says in part A, we assume M2G is beating M1G, and so the net force here, the net force here is M2G minus M1G, acting on the total mass of M1 plus M2. Rearranged for acceleration, you can pull a G to the outside, and it's all fancy. When you get M2 minus M1 quantity times G divided by the quantity M1 plus M2, or as we've done in class, M2G minus M1G all over the total mass of M1 plus M2. So that's the old way of doing things. That's when we assumed the pulley had no mass, it didn't rotate, the string just slipped on the pulley. Alright, now as it says, we're going to consider the pulley to be a solid cylinder of non-negligible mass. And now it's a massive pulley. It's got a radius capital R, and the string does not slip in the groove of the pulley, but the pulley rotates without friction from its axle. I'm literally just reading what it says in problem 4. So this is where we ended with in class with part B. What forces provide torques to the pulley wheel? To see that, really what we have to do is draw a Freebody diagram. So in the space between letters C and D, all the way on the left side of your paper, let's draw a Freebody diagram of the pulley wheel. So here's the pulley wheel. It's got a mass capital M. It's got a radius capital R, and I want you to pause the video and draw a Freebody diagram including all the forces acting on the pulley wheel. So pause it and come back to this. So hopefully, of course, you started with the weight of the pulley wheel because now it's non-negligible mass, and of course the weight acts right through the center of the object. That's going to be capital MG. And then there's got to be something supporting the system from that string, sort of connecting it to the horizontal support there. So there's got to be a tension in the string acting in the center, pulling up. And then there should be two tensions on either side. One on either side, I should say. One from mass 1 and one from mass 2. So the Freebody diagram should look something like this. Again, weight, capital MG, right through the center of the pulley. I'm calling this T3 because here's T1, the string attached to mass 1, and here's T2, the string attached to mass 2. So this, I'm just going to call this T3. If you call them different numbers, if you could just sort of restructure it now, because otherwise you'll be very confused as we go through the derivation. So we're calling T1 the tension of the string attached to mass 1, T2 the tension of the string attached to mass 2, and T3 is the one supporting the entire system. Each of these strings is touching the pulley, and so it touches the pulley perpendicular to the radius or tangent to the circular path, circle of the pulley, and so that's the only proper way to draw the tension for the string touching the pulley. So the question becomes, what forces provide torques to the pulley wheel? Well, our equation for torque is RF sine theta, R being the distance or the position vector measured from the pivot point to the application of the force. The pivot point clearly is going to be the center point because the whole wheel is going to rotate this way in a clockwise fashion. Mg points straight through that pivot point, and so just like we did in class, there's no value of R. It's not displaced from the center at all, so it provides no torque. This tension is also pointing right through the pivot point. There's no value of R for this tension. It's not displaced off to the side, so it also provides no torque to the system. Only T1, which is all the way over here, and T2, which is all the way over there, are forces that are displaced away from the central pivot point. They're the ones that can provide torques. The big misconception is that the weights of the hanging objects, M1 and M2, are providing torques. But look at our Freebody diagram. M1 and M2 are not on the picture at all. Therefore, they don't provide torques to the pulley. Only forces touching the pulley can provide torques to the pulley. So in this case, that's going to be T1 and T2. Okay, then we have to derive an expression for the acceleration of either mass. So we start by looking at the pulley, and we know that it's going to rotate this way, so we can add an angular acceleration vector, and we'll call that the positive direction. As we've done before, drawing a curved vector is not really correct, but, that's what's happening, so it's fine for our purposes here. And then, of course, we can write sigma tau equals I alpha, that a net torque of the pulley will cause this angular acceleration based on the moment of inertia, or the rotational mass of the pulley itself. But here we run into a bit of an issue. if this pulley is going to accelerate in an angular way, then the net torque has to be some value other than 0. Which means that one of these torques, either the one from T2 or the one from T1, has to win over the other. Well, how could this possibly be? They're both the same distance away from the pivot point. So the only way for T2 or T1 to beat the other is if the tensions themselves are not equal. See, up to this point, where the pulley didn't matter, it didn't move at all, we assume that the string had the same tension throughout, but clearly that can't be the case. If this tension and this tension were the same, then the torque from this one going the clockwise way, and the torque from this one going the counterclockwise way, they'd have to be equal. That would make the net torque 0, that make the angular acceleration 0, and that's just not what's happening. This pulley wheel will accelerate in this clockwise way, so the torque provided by T2 must win over the torque from T1. The only way to make that happen is for T2 to actually be larger than T1. So what we do is we go back to our Freebody diagram, let's shorten up T1 so that T2 is now clearly larger than T1, which is weird. The tension in the string is actually different depending on what part of the string is touching the pulley. Okay, so that's the weirdness of this. Now what do we do? Well, we're going to add up sigma tau. So let's do the torque from T2 is going to try to rotate the pulley in a clockwise way. That's in the positive direction. So it's RF sine theta. That's going to be positive. T1 is trying to rotate the pulley counterclockwise, which of course is in the negative direction. So sigma tau will look like this. Positive R T2 sine theta minus R T1 sine theta. So this is positive because T2 tends to rotate it in the clockwise way. This one is negative because T1 tends to rotate it in the counterclockwise way. The moment of inertia is going to be half mr squared from our chart on our notes page we did in class because, as the problem says, we're going to assume this is a disk or cylinder. That's 1/2 mr squared, and here's alpha. So this is sigma tau equals I alpha. What can we do next? Well, let's evaluate theta. Remember, theta is the angle between R and F. So for T1, the position vector is from the pivot point out to the application of the force. That's R, and here's F. For T2, here's R, and here's F. Either way, the angle is going to be 90 degrees, and we know sine of 90 is 1, so we can just take the sine theta out of the equation. So now it's just RT2 minus RT1 equals half mr squared alpha. And now we're going to play the same trick we did in class when we had the pulley with a single block falling off of it. We know that if you identify any point along the rim of the pulley, it's going to have a tangential acceleration. So if we look at this point right here, its tangential acceleration will point straight down. That's going to be the same as the tangential or linear acceleration of this mass that's hanging there. And so we can relate these two by saying A equals R alpha, or the tangential acceleration of this point is related to the angular acceleration by this connecting equation A equals R alpha. We saw this for alpha as A over R. We can plug it into the equation. Alpha is A over R right here. And now look what happens. This factor of R will cancel one factor of R here, leaving one factor of R on the right. But there's a factor of R on the left that will cancel the remaining factor of R on the right. And so all the R's go away. And so we're left with this. T2 minus T1 equals 1/2 MA. At this point, it's not a bad idea to pause the video and really go through and make sure you understand how we built up this sigma tau equation, why T2 has to be larger than T1, where this equation for I came from, reminding yourself how we got this equation, how we substituted to here, and how we canceled all the values of R. So pause the video, make sure you're good on that before moving on. Alright, so at this point we have this equation relating the tensions to something with the acceleration of the pulley, or the linear acceleration or point on the pulley. But we can't be done because there's too many unknowns. So next thing we do is we look at the individual objects, M1 and M2. So I want you to pause the video, I want you to draw Freebody diagrams for both M1 and M2, and build up the equations for sigma F equals MA for each one of these. Let's start with M1. Of course, we have weight pointing straight down and tension pointing straight up. Who is winning? Well, we know that M1 is going to lose in the overall rotation of the pulley, so M1 is going to be moving up and accelerating up. So we know, of course, T1 is going to be larger than M1G. The opposite is true for M2. Obviously, M2G points straight down and T2 points straight up, but since M2 is winning, because the whole system rotates clockwise, M2G has to beat T2, so make sure you're drawing M2G larger than T2, and pause the video if you need to restructure right now. And then we're going to write sigma F equals MA for each of the objects. So for the left one, or M1, it's sigma F equals MA. And of course, since up is positive, I assume we're calling up positive. T1 beats M1G, so it's positive T1 minus M1G equals M1A. For M2, down is positive because it's moving down, and so sigma F equals MA will look like this. M2G minus T2 equals M2A, and if you mess that up, please pause the video. At this point, you really should be very, very clear that whichever force is winning, you usually call that the positive direction, since this one's moving up and this one's moving down, so T1 beats M1G, and here, since it's moving down, M2G beats T2. We can't, at this point in the year, be messing that up. It's not a guessing game. We have a structure, a routine that we follow. So what do we do with these? Well, this equation has both T2 and T1. These equations have T1 and T2. Why don't we go ahead and solve each of these for their respective tensions? So pause the video, manipulate these. So solve this for T1, solve this for T2. So this should look like this. T1 equals M1G plus M1A. This one looks like T2 equals M2G minus M2A. And now it's just algebra. So you can take this whole expression for T1, plug it right in here for T1. Take this whole expression for T2, plug it right in here for T2, mix and match, and you're going to solve for A. So pause the video, do all that algebra, and come back to the video to see how you did. So here's what that should look like. Here is T2, which is M2G minus M2A, right from here. Here's T1, that's over here, M1G plus M1A. Make liberal use of your parentheses so you can see the minus sign is part of this equation we derived here, so we have to then distribute that negative sign all the way across. A good next step is to get everything with A all over to one side, and then since you're solving for A, you can flip it around. So the next step would be half MA plus M2A plus M1A equals M2G minus M1G. And be very careful with your signs. It's just algebra here. You really shouldn't be losing any signs or doing anything wrong with this, but check your work against mine and make sure you're getting it right. You can factor A to the outside, and in the end, we should have this. M2 minus M1 quantity of G times G divided by this whole mass here, M1 plus M2 plus half the mass of the pulley. Let's do a side-by-side comparison. If you look back to part A, here was the acceleration when we didn't consider the pulley rotating. It looks very, very similar. In fact, it's still the same driving net force on top. All that really happens is we have this extra term of half the mass of the pulley entering into the total mass. Now, you couldn't have predicted it to be half the mass. That only happens because of the moment of inertia equation for this rotating disk. It happened to be the same one as we did in class, the extra factor of half mass, because that was also a rotating disk. If it were any other shape of object, whatever coefficient, whatever fraction goes in front of mr squared, that's what would show up here. So this is not a new equation. It's, even though it shows up twice with that half m and this one, the one we did in class, it's still not a new equation. You'd have to go through all these steps to get to that equation. At this point, go ahead and do part D, where the numbers are given, and you can plug them in and see if you can just recover those answers, just to get a sense of the acceleration of the pulley, of this system, considering the mass of the pulley, or when we don't consider the mass of the pulley, just so you can see the effects of it. You'll also see, by putting the numbers back in, that you will get that the tensions are different, that T2 must be larger than T1. Again, that has to happen, which I know is kind of weird, but it has to happen, so we will achieve a net torque, so the pulley will accelerate in a rotational sense.